Welcome to a screencast on characteristics of exponential functions. Let f of x equal b to the x, where b is a positive constant and b does not equal 1. We call f of x an exponential function with base b. Notice that f of 0 equals b to the 0 power, which equals 1. This tells us that the graph of f of x passes through the point 0, 1. Additionally, we stated that b is positive, and we know that a positive number raised to any power is always positive. For example, 3 to the 5th equals 243, and 3 raised to the negative 5th power equals 1 over 243. This tells us that the output of any exponential function of the form f of x equals b to the x will be positive. In other words, the graph of f of x is never 0 and thus has no x-intercepts. As we have done with other functions, we will explore the effects of applying transformations to the exponential function f of x equals b to the x. Let g of x equal ab raised to the x power, where a and b are both positive constants and b does not equal 1. Based on our earlier work with transformations, we know that g of x is a vertical scaling of f of x equals b raised to the x. We call the base b the growth factor of g. In addition, given a growth rate r of a function, the growth factor b is given by b equals 1 plus r. As a result, we can think of g of x equals ab raised to the x as g of x equals a times 1 plus r, quantity raised to the x. Let's look at a couple of examples to better understand the relationship between the growth factor and the growth rate. If h is growing at a rate of 30%, then the growth rate is written as a decimal 0.3, and the growth factor is b equals 1 plus 0.3, which equals 1.3. In the case where the growth factor b is greater than 1, we say function g is exhibiting exponential growth. We should note that b is greater than 1 because the growth rate was positive. Now, if function k is depreciating at a rate of 30%, then the growth rate, written as a decimal, is negative 0.3. The negative indicates that k is depreciating. Then the growth factor is b equals 1 plus negative 0.3, which equals 0.7. In the case where the growth factor b is between 0 and 1, we say the function g is exhibiting exponential decay. B was between 0 and 1 because the growth rate was negative. Now let's make note of the different properties of g of x in both cases, when there is exponential growth and exponential decay. So again, we'll let g of x equal ab raised to the x power, and on the previous slide, we saw that when the growth factor b is greater than 1, the graph exhibits exponential growth. We also saw that the growth factor b, which equals 1 plus the growth rate r. So when r is positive, the growth factor will be greater than 1. When the growth factor b is greater than 1 and there is exponential growth, the graph will always be increasing and concave up. Now let's look when the growth factor b is between 0 and 1. Then the graph exhibits exponential decay. On the previous slide, we saw that because the growth factor b equals 1 plus the growth rate r, when r is negative, the growth factor will be between 0 and 1. So the growth factor b between 0 and 1 with a negative growth rate r indicates that function g will exhibit exponential decay, and the graph will always be decreasing and concave up. In both cases, we can find the y-intercept by evaluating g of 0, and we find that ab raised to the 0 power equals a times 1, which equals a. So the y-intercept of g of x is 0, a. Because the growth factor b is always positive, and a positive number to any power is always positive, the range is all positive real numbers for both exponential growth and exponential decay. Lastly, the domain of any exponential function is all real numbers. In future videos, we will learn how to determine formulas for exponential functions and explore trends in exponential function behavior. Specifically, we will look at the relationship between concavity and the average rate of change of a function.